Hello, Honors Algebra 2 students, and welcome to Wednesday's lesson number 33 on complex numbers. All right, so I'm going to give you a little warning here. This is a very complex topic. It is incredibly interesting, and it is incredibly abstract. Let's go through the vocabulary of what we're doing today, and I'll get into what is so strange about today's topic in just a moment. So, today's goals. We're going to perform operations with pure imaginary numbers. We're also going to perform operations with complex numbers. Now, these imaginary numbers and complex numbers, these are a new type of number system. Just like negative numbers at some point were a new type of number system to you, which you may never have heard of before, and which may never have meant anything or seemed meaningful at all, we have a new set of numbers that we're going to talk about today. So I want to hone in on that negative number analogy again. There was a very long period of time where no one ever used negative numbers. If somebody was to write down an equation that said 5 minus 7, that person would be probably laughed at because it's just so painfully obvious that you can't take 7 things away from 5 things. No matter how hard you try, you only have 5 to work with. However, at some point, somebody came up with this new number system. They said numbers don't start at 0 and go up 1, 2, 3, 4, 5. Let's see how high you can count. They actually go below 0. And speaking of 0, 0 was also a number that didn't always exist with the rest of them. That took somebody's a leap of courage to kind of create a new type of way of describing the world. So our new type of description for the world is a description that satisfies the following problem. What is the square root of a negative number? Now, if you've never heard this before, this may sound a little strange, so let's take something that makes more sense. What is the square root of a positive number? Let's say, what's the square root of 25? Well, you might think 5. Yep, 5 times 5 makes 25. And if you are really on top of things, you might go, also, there's another one. Negative 5 is a square root because negative 5 times negative 5 equals 25 as well. So with that, we can say, okay, any positive number is going to have 2 square roots. Now, any number squared, any real number, any number from 0 to infinity or 0 to negative infinity, if we square it, we will get a positive number. So how is it then that you could take a negative number and find a square root? There shouldn't be any answer. So for example, if I said, what's the square root of negative 25? There's no number that I can think of, no real number that allows me to multiply that number by itself and end up at negative 25. It's the negative part that's the problem, the square root of the negative. Now, it was about 400 years ago, so in the 1600s, same time as like scientific revolution and the Enlightenment are kind of taken off for the first time. There was an Italian mathematician who just decided that he was going to come up with an answer to that question. He just decided that the square root of negative 25 did have an answer. And he was going to imagine what that answer was, and it was going to be a whole new type of number. Basically, he just chose that there was a solution. He defined his solution, and he gave it a name. He called it I. Now, that wasn't the square root of negative 25. That was the square root of negative 1. And that is kind of where we start. So the imaginary unit I is the square root of negative 1. Okay, so let that sink in for a moment. You have negative 1, and you say, what is the number that times itself gives me negative 1? Well, since I can't think of any real number, I'm just going to imagine one. And we're going to call that the imaginary unit I. Now, a lot of people find that term imaginary to be kind of irritating because it suggests that it is less of a real concept than the real numbers are. But there's a sense in which you could say that negative numbers are pretty unreal in a certain sense. To say that I have 5 apples and I take away 7 and now I have negative 2 apples, you're never going to be able to point to negative 2 of something. And you're never going to be able to point to I units of something either. However, -2 is a very useful concept, and I turns out to be a very useful concept too. Now, if you're curious, the uses, it usually comes in certain fields of engineering or chemistry and physics and quantum mechanics. The short version of it that I can kind of summarize is that it helps with something called vector multiplication, which is where you are trying to see what is the product of two things that have both an amount, like a size, and a direction. So on graphs, that kind of looks like arrows drawn on graphs and the multiplication of those arrows. All of this may seem very complicated and confusing, but we're going to work through a series of examples, and I promise you that if you follow along, you will be able to solve these problems and you will be able to work with it. Now, my initial explanation here is limited by my own understanding, one thing, of course, and another thing would be our limit of time. We don't want to spend all day on this, even though I think this is an incredible topic and I would love to teach this topic for a month if we could, but we don't have that amount of time. If you want to get a really, really good explanation of this topic, go down to the very bottom video. There's a bonus video. It's very long. It's like an hour and a half, I think, but it's by a YouTuber who is a YouTuber for math for his full-time job. He has the ability to create really, really good diagrams and visualizations, and it really helped me understand this myself. So if you find this topic interesting, which I really hope that you do, I would suggest that you find your way there over time. Okay, I'm going to read this description that they have in the book, and I'm going to remind you that this is going to be too quick of a description to really get the point across, but we'll read it anyways. Okay. In your math studies so far, you have worked with real numbers. However, some equations, such as x squared plus x plus 1 equals 0, do not have real solutions. If you imagine that parabola, it would be sitting above the x-axis. It would never touch 0. Doesn't have a real solution. Okay, this led mathematicians to define imaginary numbers. The imaginary unit I is the principal square root of -1. Thus, I equals the square root of -1, and I squared equals -1. Numbers of the form 6i, -2i, or I root 3 are called pure imaginary numbers. A pure imaginary number is a number of the form bi, where b is a real number, like 6, -2, or the square root of 3, and I is that square root of -1. For any positive real number, the square root of -b squared equals the square root of b squared times the square root of -1. That's just factoring a radical. You'll see an example of that pretty quick here, or bi. The commutative and associative properties of multiplication hold true for pure imaginary numbers. That basically means that the types of things that you're used to doing with real numbers, you can do the same things with these imaginary numbers. The first few powers of I are shown. So I to the first power is just I squared is -1. I cubed would be I squared times I, or -1I. Okay, all right, so that is your introduction there. And I wish you luck, and I hope that you enjoy this lesson and the examples we worked through.